So, what we are trying to discuss with these articles, key what is the sensing principle to sense a particular thing and why we want to measure some stimulus. For example, using Hall effect, what we want to sense means what property we are discussing here means deflection of path of moving electrons. So using that, we can sense something. And based on this principle, we can design a sensor to sense something, to sense numerous stimulus. Okay. So that was related to Hall effect. So using the the transverse Hall potential, we can design a sensor and we can sense various type of stimulus. Now, another important principle based on the sound waves. Sound waves, as we know, what is sound wave? So briefly, we will describe here the alternative physical compression and expansion of medium, maybe solid, liquid, and gas. The certain frequencies are called sound waves. So, at a regular interval of time, if there is alternate physical compression and expansion of medium, then this phenomena produce uh, sound waves. The medium contents oscillates in the direction of wave propagation. Means in this phenomena, what happens? The contents of the medium they oscillates in the direction of wave propagation. Hence, the produce sound wave. It is termed as longitudinal mechanical wave. So these sound waves are the longitudinal mechanical. Longitudinal wave, those are propagating. Their particles are oscillating in the direction of wave propagation itself. So that's why it is termed as longitudinal wave. The name sound is associated with the hearing range of human ear, which is approximately from 20 hertz to 20 kilohertz. So this is the range of frequency of human ear can hear. Okay, so we can hear from 20 hertz to 20 kilohertz frequencies. And if same experiment is performed for uh, other animals, uh, then the frequency may be wider. But for human being, this is the range. And from this range, whatever the wave we have, we can term it as a sound wave. Okay. So there is one difference between the sound wave and the voice of human being. Means that I am talking, you are listening, although a complex media is involved, but if you are in the class, then if I deliver a lecture, all you will listen my lecture through a movement of air particles. So that comes to you through sound wave. But that frequency is not from 20 to 20 hertz to 20 kilohertz. That is limited only to 30 or 20 hertz to maximum 3400 hertz. Okay. So the sound waves, they ranges from 20 hertz to 20 kilohertz. Now, if we look at the sound waves, those are below 20 hertz or above 20 hertz, 20 kilohertz. Okay, the sound waves, those are below 20 hertz, they are termed as infrasound waves. And those are above 20 kilohertz frequencies, they are termed as ultrasound waves. So detection of infrasound is of interest with respect to analysis of building structures, earthquake prediction, and other geometrical large sources. Okay, so for if you want to see analyze a building structure, if you want to see maybe the defect in that, maybe something else, maybe strength, maybe anything related to the structure. So if you want to perform the analysis of building structures, then the detection of this infrasound is very important. Similarly, for earthquake predictions and other geometrically large sources. So the ultrasound uh, infrasound detection is very important for these categories. Now, when infrasound is of a relatively strong magnitude, if its amplitude is very large, but frequency is less than 20 hertz. Okay. So the human ear means we cannot hear the sound. We cannot hear it. But at least human being can feel it by producing a quite irritating physiological effects. Uh, for example, panic, fear, etc. Sometimes, if anyone face these type of problems, then we may assume that our body sensor senses something whose magnitude is large enough, but frequency is less than 20 hertz. So if we want to determine these type of stimulus, then we can take this sound wave as a mechanism by which we can measure, or we can measure different type of stimulus whose frequency is very, very less. Okay, so that's why we are discussing different sensing principle here, and these principles can be involved in different types of sensors to sense different stimulus. Now, related to this sound wave, how we can define the sound wave, how we can mathematically model it. So we can define the intensity of sound wave by I. I is the intensity, and what is the meaning of intensity? It is nothing but the power transferred per unit area. Means how much power we are getting in per unit area, then that we will term it as the intensity of sound wave. So this is a common, but however, to specify sound not by intensity but rather by a related parameter beta, and this beta is called the sound level and defined with respect to reference intensity I naught. This is the reference intensity of sound wave, and its value is 10 to the power minus 12 watt per meter square. And beta, that is the sound level, it can be defined in dB, decibels, as 10 log 10 I by I naught, where I is the intensity of sound and I naught is the reference intensity of sound. The magnitude of I naught was chosen because it is the lowest ability of a human ear. The unit of beta is decibel. So if I is I naught, means the actual sound produced by a source has intensity that is equals to reference intensity value, then beta will be 0. And what is I naught? I naught is the reference intensity, and it is the value that a human ear can measure, can observe. So this is the lowest value. So that's why it is reference level. So with this, what we can say, we can measure some intensity of sound, and if we have something by which we can measure, we can say this much of sound will be produced by this source. So we can detect it, we can design a sensor like that. Correct. Now here we have a table in which different sound levels are given. Uh, One more thing I want to tell, the response of a human ear is not the same for all the frequencies. And at different frequencies, sound levels are usually different. Okay. So here in this table, what is shown here, the sound level uh, reference to the reference intensity I naught, but at a particular frequency, that is 1 kilohertz. So at 1 kilohertz, these values are mentioned in the table, means how much a particular source produce beta in dB. So example, suppose if we look at the rocket engine and at a distance of 50 meter, then it can produce a sound level of 200 decibels at 1 kilohertz. Means this is corresponding to 1 kilohertz frequency only. If frequency is different, the sound level value will be different. So if I want to know the intensity of a rocket engine produced at a distance of 50 meter and corresponding to frequency of 1 kilohertz, if you put this value in that expression, beta equals to 10 lakh 10 I by I naught. Beta is 200 dV. Okay. So 200 by 10 means 20 dV, and take the inverse log. The 10 log 20 equals to I by I naught. So I naught will be, sorry, I will be equals to I naught into 10 raised to the power 20. And what is I naught? I naught is 10 raised to power minus 12 watt per meter square. So 10 raised to power minus 12 into 10 raised to power 20. So that is equals to simply 10 raised to power 8 watt per meter square. Now look at the sound power generated by this type of engine. It's very large intensity. Okay, so in this way we can look at different values, and the important thing is at the last, the threshold of hearing, it is 0 dB. So if a source that produces sound whose beta is 0 dB, human ear can detect it. This is the minimum reference value that can be detected by human ear. If it is less than that, means less than that means what? Can beta be negative? May be negative when I means the source that is generating sound wave, that is generating sound signal, whose intensity is less than below the reference value Y naught. Then it cannot be heard by human being, and beta will be negative. We cannot hear it. But don't say it is infra. Why? Because its frequency is not less than 20 hertz. Its frequency is still 1 kilohertz. Okay. So at any frequency it can happen, but in that sense, in that case, what we will say, the source that is producing the sound wave, its intensity is below its reference value that can be heard by a human being. Okay, in that case, beta may be negative. So we have different values of sound level as shown in this figure. Okay, so what we can do, we can design some sensors to sense these signals. Now this is the sound wave. Now sound wave can propagate through a gas, through air, through any liquid, through any solid. So we can measure different types of stimulus by measuring these quantities, and we can design different sensors that could be capable to measure the sound level, sound intensity, etc., etc. Correct. So we can decide this stimulus. Uh, this is the value of the given stimulus. Okay. So this is another principle of sensing the intensity of sound wave by any means. Another important thing, the sensing mechanism, that is the light. Okay. So from light we can sense many types of stimulus. Okay. So light is very efficient form of energy for sensing a great variety of stimuli like distance, motion, temperature, chemical composition of an object, or many more. Light has an electromagnetic nature. It may be considered a propagation of either quanta of energy or electromagnetic waves. The different portion of the wave frequency spectrum are given a special name. For example, ultraviolet light, visible light, near infrared light, mid infrared light, far infrared, microwave, radio waves, millimeter waves, X-rays, gamma rays, like that. Okay. So the different names are given. And these frequencies definitely have some energy. Uh, so the frequency and power, both things they have. The name light was arbitrarily given to electromagnetic radiation, which occupies wavelength from approximately zero point 0.1 millimeter to 100 millimeter. Light below the shorter wavelength that we can see, what is the shorter wavelength? That is violet. Is called ultraviolet, and the farther that the longest that we can see is red, and which is called infrared. So the lowest one means the light that when we can see is violet, below which it is ultraviolet, and after red it is infrared. Okay. The infrared range is arbitrarily subdivided into three regions. This is purely theoretical thing, so please go point by point. Don't worry about it. We will discuss interesting thing that just after covering these theoretical things. Means we at least we should remember the range of different ranges of frequencies, different frequency ranges associated with different spectrum. That is our aim. So the infrared range is arbitrarily subdivided into three regions. Near infrared from zero point 0.9 to 1.5 millimeters. That is what the wavelength of the particular frequency, particular wave, a light wave. The mid infrared, it ranges from 1.5 millimeter to 5 millimeter. In far infrared, ranges from 5 to 100 millimeter. Entire electromagnetic spectrum is represented in a figure we have in the next slide, and it spreads from gamma rays, the shortest, to radio wave, the longest. Now come to the some properties of light. The velocity of light in vacuum, we know that it is 300 meter per 3.8 into 10 to power 8 meter per second, or roughly given in by this value, but it is independent of the wavelength that can be expressed through an expression C naught equals to 1 by square root of mu naught and epsilon naught. Mu naught, epsilon naught, they are termed as the magnetic and electric permittivities of free space. Okay. So they have fixed values. They have fixed values. Permittivity of electric permittivity of free space, that is epsilon naught, it is having fixed value, and the magnetic permittivity, that is mu naught, it is also having fixed value. Mu naught and epsilon, if we put the value, we will have this velocity of light in vacuum, means no hindrance is there. It is constant and approximately equals to 3.8 into 10 to the power 8 meter per second. Correct. Now this figure shows the, as I mentioned here, the spectrum representation of electromagnetic waves. So here the spectrum of electromagnetic wave is represented starting from radio waves, AM radio, very low frequencies. Here the low frequency, here low wavelength. So in this way, frequency low, frequency high. And if we come from left to right, then wavelength low, wavelength high, like that. So wavelength in meter and frequency I didn't mention, but here it is the frequency. Okay, so wavelength, it is decreasing. Right? So wavelength decreasing means frequency increases. Correct? So from 0 to maximum, like that. You can say frequency range, if we start from here, so maybe 0 hertz here and then maximum here. Wavelength in reverse order, the minimum wavelength, maximum. So different spectrums are shown here. AM radio waves, then short waves radio, TV and FM radios, the microwave radio, radar frequencies, millimeter waves. Okay. Then after that, thermal radiations. Those thermal radiations, it is invisible range, means it's not visible to human eye. Then visible range, visible light from violet to red, waves, and then ultraviolet, then X-ray, gamma ray, etc. So with this, what we can do means we have the speed of light, means the velocity of light in vacuum as C naught. So the frequency of light wave in vacuum or any particular medium, it is related to its wavelength. This is the frequency of light wave, represented by nu. It is equals to C by lambda. This is frequency where C is the speed of light in a medium. It is not the in vacuum. Okay. So the with this, what we can say, the energy of photon relates to its frequency given by E equals to h nu. Nu is the frequency of photon or the light wave, and E is the energy associated with that photon or light wave given by this expression h of nu, where h is a Planck constant that is having constant value. The photon energy is measured as 1.6 into 10 to the power minus 19 joule. All it is equals to 1 electron volt. That is for a photon. Okay. The ultraviolet and visible photons carry relatively large energy and are not difficult to detect. Means if ultraviolet signals or visible photons, uh, because of their large energy, it's easy to detect them. However, when wavelength increases and moves to an infrared portion of spectrum, not from the ultraviolet, this is infrared, the detection becomes more and more difficult. It follows from E equals to h nu that energy of quanta drops for a lower frequency. So if energy drops, then it's not possible to detect that photon. A near infrared photon having a wavelength of 1 millimeter has the energy of 1.2 electron volts. Hence, an optical quantum detector operating in the range of 1 millimeter must be capable of responding at the level of energy. Means with the help of optical quantum detector, we can detect it, this photon. Uh, the quantum detectors, they are semiconductor devices. When light strikes on that, then because of absorption of energy, they generate the secondary electrons, and that the secondary electrons moves in the material and produces some energy. So the light energy is converted into electrical signal. So in this way, we can design the quantum detector to detect the energy of these signals. So if we keep moving even further towards the mid and far infrared spectral ranges, we deal with smaller energies because higher frequency, smaller energies. Okay. If we consider the human skin at 37-degree temperature, 37 degree Celsius temperature, it radiates near infrared photons with energies near to 0.13 electron volts, which is an order of magnitude lower than red light, making them much more difficult to detect. Means that energy we cannot easily detect. But if we can detect, we can measure several stimuli related to this human body. Okay. So this is the reason why low energy radiation is often detected by thermal detectors rather than quantum detector. Now for detecting these, we need thermal detectors. Nowadays we have different types of detectors. They can detect the several things associated with the human body. Means without inserting anything, the heartbeat, heart rate, oxygen level in our body, and many more. They can be detected. So based on this, uh, the sensing principle. Which sensing principle? Light sensing principle. So by sensing the light, we can determine several stimuli or excitation. For example, heartbeat. For example, oxygen level in our blood.